Okay, our next speaker, we're very excited to have Alexandra.
Hi. Yeah, so thank you so much. Hi, everyone. I'm Alexandra. I'm a grad student here in the department, and I'm going to talk to you today about new constructions of somewhat homomorphic encryption. And this is joint work with my advisor, Henry, and with Yael and Vinod. Okay, so the classic problem solved by cryptography is that of secure communication. So in this problem, my friend and I want to communicate, but we can only talk over some public or insecure network. And the way cryptography solves this problem is by letting me sample an encryption key that I can share with my friend. And now we can send encrypted pieces of information over this network so that each of us can decrypt the packets and see what the information is. But to anyone who's just eavesdropping on our messages, they have no idea what we're saying. A downside here, though, is that this fundamentally requires trusting the recipient. So here, for example, I trust my friend, but this isn't always what we want to do in the real world. So in the real world today, we're sending our personal data all over the place to many, many recipients, and it really only takes one of them to be breached, compromised, or malicious for our data to fall into the wrong hands. And so what we can do is we can ask whether we can ask for more from cryptography, and specifically whether we can protect our data not just during communication, but even during computation. And so cryptographers have formalized this notion of that as that of homomorphic encryption. So the idea here is that in a homomorphic encryption scheme, anyone can compute directly on encrypted data without ever decrypting it and without ever learning what the underlying data is. So to be a little bit more precise here, again, I'm going to sample a secret encryption key. And now I can encrypt any values of my choosing. So here I'm encrypting these values x1 through xm. And I can publish them in a way that any recipient, so here, for example, this server, can apply a function directly to the encrypted data without ever decrypting and without ever learning my messages. So here, for example, the server is going to produce the encryption of f applied to x1 through xm. So to be just a little more formal, we say an encryption scheme is homomorphic if it satisfies three properties. So first of all, if our encryption scheme is correct, which really just means that given the secret key, I can decrypt the server's message here, and I'm correctly going to recover f applied to x1 through xm with good probability. So second, we need our encryption scheme to be secure, which means that anyone who does not have my secret key has no idea what the messages are that these ciphertexts encrypt. And finally, we want our encryption scheme to be compact, which really just means that the bit length of all of our ciphertexts here should be a fixed parameter and really should not grow with the function f that we're applying to them. And really, the intuition for this last requirement here is that what this protocol here is doing is it's sort of outsourcing the computation of f to the server. So it had better be that the communication that we're incurring is smaller than if the server were just to send us f in the first place. So really, this compactness here captures what we mean to actually compute on the encrypted data. Okay, and so a long and very fruitful line of work has shown that if we have homomorphic encryption, then we can use this to build a whole suite of privacy-preserving applications. So for example, you could imagine that the function f here is a machine learning model, and so we can have our user make private queries to the machine learning model without revealing what she's querying the model on. Or similarly, you could imagine f here to be web search or like the Google functionality. And then in that setting, you can use this to build a private search engine that never actually learns what its users are searching for. Okay, so this is homomorphic encryption. And so sort of as the definition implies, homomorphic encryption exists along a gradient depending on what types of functions we can actually apply to encrypted data. So at the very bottom here, I have classic private key encryption, which is not homomorphic, so we can't perform any computations on encrypted data. Then above this, we have linearly homomorphic encryption, which can evaluate only linear functions, so perform only additions on encrypted data. And then at the very top here, most powerful, we have fully homomorphic encryption, which can evaluate any function on encrypted data. So really, for the purposes of this talk, you should think of this as evaluating any number of additions and any number of multiplications on ciphertexts. And so really, in between linearly homomorphic encryption and fully homomorphic encryption, there's a huge range, depending on how many multiplications your scheme can support, so really how expressive the function class is that it can handle. And we generally refer to this as somewhat homomorphic encryption. OK, so what do we have today? Well, the classic encryption schemes that we use every day to protect our communication on the internet are not homomorphic. But fortunately, we can do better. And so specifically, the number theoretic cryptography of the 1980s gives us a whole suite of linearly homomorphic encryption schemes. And a really beautiful line of work showed that you can actually boost these schemes to compute some nonlinear functions. So specifically to compute branching programs of a certain type on encrypted data. Then in 2005, we learned that using cryptographic pairings, you can compute any number of additions and one multiplication on encrypted data. So this here is really degree 2 polynomials. And then in 2009, there was a huge breakthrough in cryptography that showed that using lattices, we can actually get all the way to fully homomorphic encryption. And today, we also know how to get there using the machinery of indistinguishability obfuscation. So really, this is the landscape of homomorphic encryption today. So if we want to compute somewhat complex functions and nonlinear functions on encrypted data, we really only have a few ways of getting there. And for the schemes on the right here, you should think of them as relatively heavy cryptographic machinery that, like rockets, can be somewhat expensive. And so this talk is going to be about a new construction of somewhat homomorphic encryption. And specifically, we're going to build an encryption scheme that lets us compute a fixed and bounded number of multiplications, followed by many additions on encrypted data. And so to build this scheme, we're going to combine two tools. So first, we're going to take a linearly homomorphic encryption scheme. So this is the balloon here given to us by number theoretic cryptography. And we're going to show how to lift a linearly homomorphic encryption scheme into a somewhat homomorphic one by using just one additional assumption. And this assumption here, on its own, just gives us private key encryption. So on its own, it has no homomorphism. But when we put these two relatively simple tools together, we get something that's much more powerful. And so that's exactly what this talk is going to be about. So we're going to see how we can combine this sparse learning parodies with noise assumption, which is the assumption that only gives us private key encryption, with a linearly homomorphic encryption scheme to build somewhat homomorphic encryption. And so specifically, the somewhat homomorphic encryption that we'll build today is such that for any a priori fixed parameter L, that's at most polynomial in our security parameter, we're going to be able to perform just slightly less than log L multiplications, followed by log L additions on encrypted data. OK, and so let's begin by discussing this sparse LPN assumption. So the sparse learning parodies with noise assumption is based on the following problem. So say I sample some random matrix A that's sparse. So specifically, every row is just going to have very few non-zero entries. And then I sample some dense and random vector S, say I have dimension n, and some error vector E. And specifically, I'm going to sample these errors so that most of them are 0, but with some very small probability. So here, 1 over root n, each error is going to be completely random. And so now what I'm going to do is I'm going to publish A, and I'm going to publish A times S plus E. And I'm going to ask you, can you distinguish this from just a random A and a truly random vector B? And it turns out, to the best of our knowledge, the answer here is actually no. So this is a hard problem. We don't have any efficient algorithms for distinguishing between these two distributions. And in fact, this is tied to the hardness of random constraint satisfaction problems and other problems in average case complexity. OK, so first of all, as scientists here, we might be sad, right? This is a hard problem that we don't know how to solve. But as cryptographers, we can be happy because we're going to use this encryption scheme to build, or we're going to use the hardness of this problem to build encryption schemes. And specifically, today we're going to use it to build a somewhat homomorphic encryption scheme. And so the way we're going to build this scheme is using two key design steps. So in a first step, we're going to use this sparse LPN assumption to construct an encryption scheme that's going to let us perform a bounded number of homomorphic additions and multiplications. So this already sounds great, right? This is what we wanted to construct. But this is going to have a huge caveat, which is that our ciphertexts are going to be huge. So really, our scheme is not going to be compact, and it's not going to meet our definition of homomorphic encryption. But it's still going to have one nice property, which is that to decrypt these ciphertexts, we're only going to need to apply a linear function. So decryption here is only going to require additions. And so then in a second step, what we're going to do is we're going to use a linearly homomorphic encryption scheme. So this is one that can perform only additions in a compact way on encrypted data to shrink down the ciphertext in our original scheme. And so now what I'm going to do is I'm going to step through each of these two ideas in much more detail. So specifically, our goal in this work is going to be to build an encryption scheme that meets the following properties. So what we would like is for our ciphertexts to be matrices, and for our server, who here is going to apply some function f to the ciphertexts, to operate as follows. So if our server wants to add two encrypted values, it should just have to add the corresponding ciphertext matrices. And if our server wants to multiply two encrypted values, it should just have to multiply the corresponding ciphertext matrices. So for the cryptographers in the audience, this should really remind you of the Gentry-Sahai-Waters fully homomorphic encryption scheme from lattices, which here we're trying to port to the setting of code-based encryption with the sparse LPN assumption. And I'll introduce one more requirement, which is that we'd like our decryption function to be linear. So what this means is that when our user gets back this big ciphertext CF here, it should just need to apply a linear function to it, so do some additions in order to get back the underlying encrypted message. OK, so how are we going to do this? Well, the key idea is going to be the following. So as our secret key, we're going to sample a random vector s. And this should sort of remind you of the s vector in the sparse LPN assumption. And then to encrypt any value x, what we're going to do is we're going to build a ciphertext that's a sparse matrix, and that has the following special structure. So we're going to have our encrypted value x be sort of a noisy eigenvalue of this matrix, where the corresponding eigenvector just depends on the secret key. So let me be a little more precise. What I mean here is that if I have my ciphertext matrix C, and I'm going to multiply it by this eigenvector, which here will be minus s and then a 1, what I'd like is to get back roughly the underlying encrypted value x, again multiplied by this same eigenvector. So this is what it means for x to be an eigenvalue of the matrix C. And when I say noisy here is, I just mean that I'll be OK with this equation here being corrupted in a couple of locations, as long as it holds like mostly. OK, so first of all, you might ask, how are we going to do this? How can we inject this noisy eigenvalue into a matrix? And the idea is going to be roughly to do the following. So to build this ciphertext matrix C, what we're going to do is we're going to sample a random A matrix. We're going to sample a random error vector. And then as our ciphertext, we're just going to publish the A matrix concatenated with one more column, which is going to be A times S plus the errors plus our message times some function of the secret key. So really here we see that what the sparse LPN assumption tells us is that A times S plus E looks random. So this ciphertext here really is hiding the message that we embedded into it. But if you stare at it for a while, you can see that it actually satisfies this noisy eigenvalue equation. OK, so what I argued so far is that we can actually build ciphertexts of this form. And now you might wonder, why is this useful? Why do we want this special structure? And the reason really is because it's going to let us perform these homomorphic operations. So specifically, to add two encrypted values, what we're going to do is we're just going to add the corresponding ciphertext matrices. And what we see is that if we add two matrices that have the same eigenvector, this has the effect of just adding their eigenvalues. So really what we get out of here is an encryption of the sum of the underlying messages. And in exactly the same way, we can multiply ciphertexts. So specifically, if we multiply two matrices, what we get out here is a matrix whose eigenvalue is the product of the underlying eigenvalues. So really, by multiplying two matrices, we get out a ciphertext that encrypts the product of their two messages. And last but not least, I said we wanted decryption to be linear. And again, this here follows by this same blue equation. So specifically, to decrypt a ciphertext, all we need to do is to multiply it by this secret vector, which has the negative s and a 1. And what this gives us is the message multiplied by the same vector. So we can then check whether the underlying encrypted value was a 0 or a 1. OK, so that, yeah?
Linear, right? It's linear with noise.
Linear with noise.
Linear
Exactly. Well, so for our purposes, it's going to be linear because we're just going to look at one location in this equation, and we're going to just guess that it has no noise. But you're totally right. You could do some error correction here. Like you could compute some majority function, but we just won't do that for our purposes so far. Great. OK. So now, zooming out again, we have this scheme. Our ciphertexts are these sparse matrices. Our server can compute on them by just adding these matrices and multiplying these matrices. And when we do this, they get somewhat less sparse. And the errors in the underlying equation are going to propagate somewhat. But if we sit down and analyze this, we see that if we have our initial matrix dimension be n by n, and if we have our initial error rate be something like 1 over root n, then we get a scheme that actually can perform just slightly less than log n multiplications and just slightly less than root n additions, and we'll still be able to decrypt correctly. OK, so far this seems great, right? We can just pick our parameter n to be as big as we would like to support as many operations as we would like on these ciphertexts. Unfortunately, though, what I just said should be a huge red flag to you, because n here is also the dimension of our ciphertexts. So what I said is that we have to make our ciphertexts bigger if we want to compute on them more. And so in fact, we have a scheme that's not at all compact. And it turns out our server would always be better off just sending a description of the function f to the user instead of operating on these big ciphertexts whose size must be bigger than the description of f, and then sending back another big ciphertext, again, whose size is bigger than just the description of f. OK. So that's the bad news. But the good news is we've only used one of our 2 ingredients here, and we're going to try and save this using linearly homomorphic encryption. And so specifically, what we have right now is a scheme where we have these big, bulky, sparse LPN ciphertexts that our server can compute on, right? So our server can go from an input ciphertext, evaluate some function on it to get an output ciphertext that now encrypts the function applied to the data. And really, what we would like is a way for our server to translate this bulky output ciphertext into a new ciphertext from a compact and small encryption scheme that encrypts the same message. Right? This would be great if we could just shrink our big ciphertext into a much smaller one from a different scheme. And the way we're going to do this is taking advantage of homomorphism. So specifically, what we know is that our green sparse LPN ciphertext here has a linear decryption function. And really, decryption is just a function. So we can homomorphically apply this function to this ciphertext. And since it's a linear function, we know that this only requires performing additions. So what we could do here is we can take the secret key of our sparse LPN scheme, and we can encrypt it under a linearly homomorphic scheme. And then under this scheme, we can homomorphically run our decryption function. And so what this is going to give us, so what the decryption function does is it takes this big ciphertext and outputs the underlying encrypted message. So if we run this under encryption, what we get out is an encryption of the underlying encrypted message. So really, we've managed to translate from this scheme with the bulky ciphertext to the scheme with the small ciphertext, just taking advantage of homomorphism. And I should say this idea of sort of decrypting under encryption goes all the way back to the very first encryption schemes, or fully homomorphic encryption schemes of Gentry in 2009. OK, so now we've partially fixed our problem, right? We no longer have this big output ciphertext. Instead, we can have our server shrink it down into a small and compact ciphertext of a linearly homomorphic encryption scheme. But we're still not quite happy because we still have this big input ciphertext. The good news, though, is that we can play this exact same trick again. So specifically, what we would like our server to do is to start with a compact ciphertext from some small encryption scheme, and then have a way to translate this into a big ciphertext from our sparse LPN scheme. And what we see is that our sparse LPN scheme, by construction, we built it to be homomorphic, right? So if our sparse LPN scheme can evaluate the decryption function of this orange encryption scheme, then we're in business, and then we can indeed perform this translation in exactly the same way. So specifically, we can take the orange secret key, we can encrypt it under our somewhat homomorphic scheme. And then whenever our server gets this orange ciphertext encrypting the input value, it can homomorphically run the decryption function to get a big green, so sparse LPN ciphertext that encrypts the exact same message. OK, so now what we can do is we can put all of these steps together, and we get a final construction that looks roughly as follows. So first, we're going to have our user send a one-time evaluation key to the server. So you can think of this as just like an identity card that the user publishes to the server that it can later reuse as many times as it would like. And what this evaluation key is going to hold is going to be a chain of encryptions of one scheme's key under the previous one. So specifically, what I'm going to do here is I'm going to publish a sparse LPN, so a green encryption of the orange key. And then I'm going to publish a linearly homomorphic, so a pink encryption of the green secret key. And so now, whenever our user wants to send ciphertext to our server, what our user can do is it can send just these small and compact orange ciphertext to the server. It can have the server locally expand them into the big sparse LPN ciphertext, then use the homomorphism of these ciphertexts to compute on them, and then finally squish them back down into a small ciphertext from a linearly homomorphic encryption scheme. And so this is what our server can send back. So really what we've built here is a scheme where all of the communication that's sent on the wire, so all of these ciphertexts that are actually being sent here are tiny, and all of the computation with the big blow-up that happens from using sparse LPN just happens sort of in the server's head. OK, so this is it. We just constructed a whole somewhat homomorphic encryption scheme. And so really the takeaway from this talk is that we can combine these two relatively simple and in some sense weak primitives, so specifically the sparse LPN assumption and a linearly homomorphic encryption scheme, which is given to us by a whole suite of number theoretic primitives. And when we combine them, we can build something that's much more powerful. So specifically, we built a somewhat homomorphic encryption scheme where we can compute a fixed and bounded number of multiplications followed by many additions on encrypted data. So what I wanted to do now is just leave you with a couple open questions in this area of research. So the first question is whether we can actually make our schemes concretely efficient and practical. And really, the barrier here is this big evaluation key that we had our user send to the server, even though it's reusable. So you only need to send it once, but it would be really nice to get rid of this key. And if we were able to do this, then our scheme would already have a couple appealing properties. And so specifically, most of our server's work here was really doing these sparse matrix operations, which on their own are already a heavily optimized workload. The second question I wanted to ask is, with this homomorphism, so given that we can evaluate this class of functions, what can we build? And so here, at first glance, you might be kind of skeptical, right? This seems like a quite simple class of functions that we're evaluating here. But in fact, there's some hope. And specifically, in prior work, my collaborators and I showed that if you can homomorphically evaluate this class of functions, so many additions and maybe just a couple multiplications, and if you combine this with modern machine learning, and specifically semantic embeddings, then you can build things like private web search. So I think it's a fun time to think about what else we can build with these types of techniques. And last but not least, sort of the moonshot question here is whether we can fly even higher. So whether we can get even more homomorphism from these schemes, and perhaps even get all the way to fully homomorphic encryption. Cool. Yeah, so thank you so much, and I'm happy to take any questions.
Thanks for your talk and for the work that you put into the presentation also is really, I appreciate it, so thank you for that. I wanted to ask, you seem to be careful to say that you can do multiplications followed by additions.
Yeah.
Is it just because if you do some additions first, then the noise from the additions grows too much? Like, could you do one addition first if you wanted?
Yeah, so you totally can. You totally can interleave additions and multiplications as you want. And you're exactly right. The only thing that changes is sort of the error analysis. So both the sparsity of your ciphertext would grow differently, and the errors would grow differently. And so then you sort of need to perform some accounting of like how many operations can you still do before the errors become too large. But you're totally right. In principle, you can operate however you would like. I just gave this presentation because it's sort of a simple overview.
So thank you.
Okay,